Thank you. All right, welcome folks to our Sustainable Living series. This is a partnership with the Land Steward Program, the Master Gardeners Program, and the Jackson Soil, Water, and Conservation District. And this program was dreamt up of bringing together both folks of stewarding minds, gardening minds, going to be applicable for home use, acreage, just kind of a variety of uses. And you can collect all of the Sustainable Living series classes and be a path maker to a better world. And part of this class is an action plan list. The end of our class, our presenter has 3 action items to challenge you to. And you can go to this link here, and I will include this in your follow-up email. That will include a link to this presentation. You can go to the Sustainable Living series. This is a living document that I add in each Sustainable Living series class. It'll have the link to the recording, and it'll have those 3 action items. So you can scroll through and see our past classes, action items. There we go. All right. My name is Nicole Smith, and I am the Education Program Assistant. The Land Steward Program does not currently have a coordinator, but soon we will have some. We are in the hiring process. And so for now, I am filling in. Rachel was formerly our fearless leader. She's off to do other great stuff with the Native Plant Society. If you have any questions or class ideas, you are welcome to email me, nicole.smith@oregonstate.edu. And if you would like to hear about upcoming classes that we have, you could go, if you just Google Land Steward events, it'll take you to this Land Steward page. I'm sorry, folks that are here cannot see. There we go. Page looks like that. There will be a subscribe button on the bottom, and that's where we send out our MailChimps for upcoming classes. We don't spam you with a whole lot of stuff, just classes, things that we think would be relevant for you, just if you're interested in signing up for. In fact, what classes are coming up? We have a Green Your Garden with Gray Water, an introduction into household gray water systems. That is coming up. And we have a whole list of classes all the way through February of 2026, planned out 1 to 2 classes a month. So you'll see those pop up on the Land Steward events page here. And you'd also see other classes through OSU. So if you are subscribed, then you will get those messages. And when you get my message after class with the recording, you're welcome to reply if you need more instructions on how to subscribe. I'm happy to help folks with that. All right, and I want to welcome Alan. Alan has a PhD, taught biology and environmental. Of course, it's blocking out part of your, there we go. Taught biology and environmental science for decades at Southeast Missouri State University. In 2010, he relocated to Southern Oregon with Dr. Kathy Conway, who we also have here. They built a passive and active solar energy efficient home in the Applegate Valley, which now annually produces more energy than it consumes. In 2012, they co-founded Southern Oregon Climate Action, now SOCAN, serving as co-facilitators ever since. In Southern Oregon University, they teach a class entitled Living with Climate Change in Rogue Valley. And today, Alan is here to present for us Climate Change in Southern Oregon, Trends, Impacts, and Projections. So I'm going to switch out of here so that we can get Alan all set up on his. Thank you all for joining us. Maybe you've got your clicker and your laser
Okay.
pointer.
Okay, thanks very much indeed, Nicole. It's really a pleasure to be here. I should first apologize. If you're looking carefully, you'll see I have a stool here. The reason I have a stool is because I really don't like sitting down when I'm doing presentations. But I was lucky enough to spend New Year's Eve in surgery having a new knee implanted on the left side. And so I'm not as nimble as I generally am. Let me just check. I'm hoping everybody who's on Zoom can hear me. I don't know how I'm going to find out if you can. Okay, you can see them at the back. My normal mode for doing presentations is relatively informal. And by that, I mean, I would like you, if you have a question as I'm going through the presentation, please just to blurt it out. Don't feel you need to put your hand up, just blurt out the question, except if I'm in the middle of a sentence. And for the same thing for the folks on Zoom. And what I'm going to do when you ask a question, because the Zoom folks probably will not hear your question, I will try and repeat it. So one of Kathy's tasks here down the front is to make sure I remember to do that. So let's start the ball rolling. As Nicole mentioned, Kathy and I have been living here since 2010. We initiated Southern Oregon Climate Action Now in 2012. And so we have been very active in the climate arena for these 12 to 13 years now.
Let me reset this, Alan. Zoom folks are not seeing the presentation correctly.
Okay.
Alex, does my screen look like this screen? No.
Let me stand back.
Okay, how about now? We're good? Thank you. Yeah. All right, Alan, you're good.
Well, the remote's not working now.
When you go to share screen, you can select which one. Yeah, choose one of these. Try that.
Trying to get back to the beginning. There we go. That's good.
Oh, yeah. We're good.
Bingo. Okay, thanks very much indeed, Nicole, and tech support. As you can see, I am co-facilitator of Southern Oregon Climate Action Now. I am very, very happy to answer questions about climate issues, any kind of questions you have about climate issues. You can see my email at the bottom there, and please, if you would like to give me a call, that's okay also. So as I'm going, if you have questions, let me remind you, please just ask them. Before I get into the climate trends and projections, I want to introduce you to or remind you of the rather strange climate that we have here in Southern Oregon. When folks grow up in a place, they have a tendency to think whatever the climate is where they live, that's the way it is everywhere. But that's not the case. The climate we enjoy in Southern Oregon and pretty much the eastern United States, Eastern America, North America, Western North America, excuse me, little geographic faux pas. It's very unusual. And it's unusual in that when we look at the precipitation pattern through the course of the year, this little rascal I'm showing you is called a climograph. What you can see is we live in an area, and I know most people are going to say, duh, when I say this, in which our winters are wet and our summers are dry. Of course, our winters are cool and our summers are hot. That's not particularly unusual. It's that winter wet, summer dry feature that's relatively unusual. It's called a Mediterranean climate. If we look at around the rest of North America, we can see climographs over here, and you can see, well, of course, summer's always hot and winters are always cool, but you can see precipitation in New Orleans, Louisiana, for example, is pretty level throughout the year. If we come down here, this is Boulder, Colorado, you can see there's a sort of a wet period in what, spring, and then the amount of precipitation drops as we go through the year. And then over here, we're in New York, and you can see it's a bit drier during winter, but then rains through much of the rest of the year. So this climate, you can see it's unusual in North America, but it's also unusual across the planet. In fact, it occurs in 6 places. It occurs in the Mediterranean, and again, there's another duh, and that's why it's called a Mediterranean climate. It occurs in southwest and southeast Australia, South Africa, the Western Cape, Western South America, and Western North America. And the feature that this kind of a climate imposes on the location is a situation where every year we go through a period when the soils dry out and the vegetation dries out. And the outcome of that is fires, if they are initiated, tend to spread. And so fire is inevitable. So historically, during late summer, the soil and the vegetation dry out, the fire risk increases, and the consequence of that is, and let's think about where we live now, the forests in which we live are enjoy this combination of characteristics. They are fire prone, they're likely to experience fire. Because they've experienced fire since the Mesozoic period, they're fire adapted. And compounded on top of that, because this has been the situation for millions of years, they're not just fire adapted, they're fire dependent. So the forests require fire in order for them to stay healthy. And the risk that they face if fire is absent is those forests, our forests, will become invaded by species that are not fire tolerant. Our species tree species tend to be fire tolerant, inevitably because of that fire proneness. And when you hear about our forests getting particularly dense, that's because they have become invaded, and I'll talk about that a bit later, because of our tendency to suppress fire. What I want to do now is show you a few slides of a combination of the history and the projections for the future of the climate in this region. What we're looking at here is, you can see, I don't know whether that's very clear to you, that's Jackson County minimum, it's our annual temperature. So what we're looking at here is the trend, the tendency for the climate. This is the history. And as we come into the future, we're looking at the projections. When folks in the climate arena look at the projections into the future, what we do is we look at projections which are based on a set of scenarios. And these are now called socio-economic scenarios, where folks have looked at different kinds of futures in terms of our behavior and our economy, and projected what those different sets of behaviors, what those will do to the greenhouse gas concentrations in the atmosphere, and therefore the impacts those will have on temperature. And generally speaking, there are several different scenarios. What we're looking at here are summaries of a number of different models according to 3 different scenarios. This set of data comes from the US Geological Survey, and the blue line represents what's called the shared socio-economic pathway 2.45. This is a median projection. This involves a future in which we have adjusted our behavior quite substantially to reduce the trajectory of ongoing accelerating fossil fuel use and greenhouse gas emissions. The next line is called the shared socio-economic pathway 370. This is the line, I should say, the line is the median. So here the blue line is the median, and the range is indicated by the band of color. And here we're looking at the median for shared socio-economic pathway 370. And you can see that's illustrating a higher future temperature for Jackson County. If we look at shared socio-economic pathway 5, which is 8.5, this, you can see, illustrates a substantial increase in temperature as we go through the century. Now, I should note that when these scenarios were established, this particular scenario was described as the worst case scenario, because this was a scenario in which it was anticipated that basically we did absolutely nothing to remedy the situation, but just kept on accelerating our use of fossil fuels and the consequent emissions of greenhouse gases that result from that. Unfortunately, when we look at the trends, which we can do, because these models have been around for quite a while, it seems that we are actually following exactly that projection. And so rather than being dubbed the worst case scenario, it's now often termed the business as usual scenario. When these scenarios were developed, it was actually expected that we would be a lot smarter than that one, would at least follow that one, if not that one, if not even a better projector. But the point to make is that this future is in our hands. We don't have to follow this future. We can be smarter than this and exhibit a different socioeconomic set of behaviors, and we can reduce substantially that trajectory of accelerating greenhouse gas emissions, fossil fuel use. So this is Jackson County. This is the actual temperature in degrees Fahrenheit, as you can see. What I'm showing you now is the change. And it's based on exactly the same 3 socioeconomic pathways. But the point that I want to draw to your attention here, it may not have been quite so obvious looking at the actual data, the actual numbers, that this is compared to 1981 to 2010. So we're looking at the future compared to 1981, 2010 average. And what you can see here is if we continue to follow that worst case scenario or business as usual scenario, whichever you want to call it, the likelihood is the temperature in Jackson County is liable to go up something a little over 10 degrees Fahrenheit. Now, I tend to think in terms of centigrade, and I'm not going to assume everybody else does. But if you want to do a quick and dirty transition from Fahrenheit to centigrade, the quick and dirty way to do it is just divide by 2. It's actually 5/8, but 5/9, but don't worry about that. Just divide by 2. You can see that's pretty close. And as I'm going through looking at the consequences of the projections we're looking at, I want you to remember this. We're looking at a potential change in temperature in Jackson County of something like 10 degrees Fahrenheit compared to that 1981 to 2010 average. other folks here who live in Josephine County? Everybody's a Jacksonian, huh? Okay. Well, when I was putting the slideshow together, I wasn't sure, so I did the same thing for Josephine County. Okay, and so here you can see again the actual temperature values, again, according to those three socioeconomic pathway projections. And you can see Josephine County is pretty much the same as Jackson County. Maybe it's a little less severe by what? By maybe 1 or 2 degrees centigrade or Fahrenheit, maybe. And that may be a function of the fact that Josephine County is just a little closer to the coast. Anyhow, the point that I want to make here is whether we're in Jackson or Josephine County, the likelihood is, again, if we follow that business as usual scenario, we're looking at something like a 10-degree Fahrenheit, let's call it about a 5-degree centigrade, increase in temperature compared to that 1981 to 2010 average. In addition to just the overall trend for increasing temperature, there are other characteristics of that future temperature. And this is a trend that we're already seeing. Summers are warming faster, greater than winters. And that's another characteristic we're likely to be seeing into the future. Now, I want you to think for a minute about that Mediterranean climate that I mentioned a moment ago at the beginning. If we are likely to see summers even warmer than winters, then that is likely to exacerbate the problem, the phenomenon that I talked about of the soils and the vegetation drying out. Because being warmer, evaporation is going to be happening faster. Now we're looking at precipitation. And again, we're looking at the same three socioeconomic pathways. Now, this one is a little interesting in that if we look at the average precipitation for Jackson County going into the future, it looks as though it's pretty flat, and that's what the data suggest. However, and this is really interesting, I've shown this slide to high school kids time and time again. And what I usually do when I do that is say, can you see any trends there? And I was amazed, I think about the second time I did that, the kids noticed a trend that I hadn't previously noticed. And what they pointed out was, as we go into the future, and it really doesn't matter which one of these socioeconomic pathways we look at, what we're likely to be seeing is the dry years maybe being drier, and the wet years being wetter. So the troughs are lower and the peaks tend to get higher. So that means extreme weather conditions are likely to be exaggerated as we go into the future. And just to show you that Josephine County is not much different from Jackson County, that's illustrated here. In addition to overall precipitation, it's worth looking at snowfall. Snowfall is very interesting in that for those of us living on the West Coast, we have historically used snowpack at high elevation as our reservoir, providing us with snowmelt through summer and into fall. What we are seeing is a trend. This is a historical trend. You can see from something like the 1970s, the trend has been of decreasing snowpack. And as we go into the future, it's going to continue. And again, what we can see here is a slight difference in the projection, depending on which of those socioeconomic pathways we're looking at. You can see again, the shared socioeconomic pathway 8.5 here is showing a considerable drop in snowpack as we go through the century. Now, the point that I want to make here is what we're measuring here is not depth of snow, but the snow water equivalent. And the reason that folks record the snow water equivalent, which simply means the amount of water that's in the snow that falls, the reason that that is what's recorded is because ecologically, agriculturally, that's what's important. And so the critical factor is the amount of water in the snow is decreasing, likely as we go through the century. Josephine County exhibits a pretty much a parallel pattern, and here it is illustrated, just to demonstrate that.
Question for you, Alan.
Yes.
Do you have data on how much warmer winters will be?
It is part from the data center, from the U.S. Geological Survey, from the data center, it is possible to get that information. So yes, we can find it. I don't have it at the tip of my brain or tongue or whatever, but that's possible to identify. I want to talk very quickly now about evaporative deficit. It's an attribute that you probably don't think about. It's evaporative water deficit. And so just to explain that, what I'm depicting here is a test tube with water in it. And of course, Mr. Sun or Ms. Sun, whichever way you think of the sun, is smiling. And the sun is shining on that little test tube of water. So we have 3 inches of water in the test tube. So supposing because of the sun shining on that little column of water, 2 inches of water evaporate, what would happen is if you come back a bit later, you'd find there's only 1 inch of water in that tube. Okay? Now, if you start with only 1 inch of water in the tube, still the same sun shining down on it, you can imagine not only does that 1 inch of water evaporate, but in addition, another inch of water could have evaporated. So, how much could have evaporated totally from this one if the water were there? I'm sorry? 4? Well, it's the same sun with the same potential as here. So we had 2 inches here. So how many inches could have evaporated from here? It would be -1. Yes, it's 2 inches, exactly right. So what this little tube is experiencing is an evaporative deficit of 1 inch. Does that make sense? Okay, so now what we're going to look at very quickly is the evaporative deficit as modeled for our region. So here's the annual evaporative deficit for Jackson County. And you can see it's rising. And you can see clearly again, for those 3 socioeconomic pathways, it's rising a different amount. For the most extreme shared socioeconomic pathway, the annual evaporative deficit increases substantially. And the same is true for Josephine County. Big surprise. Now we have examined temperature, precipitation, snowpack, measured in terms of snow water equivalent, evaporative deficit. Now we're in a position to ask the question, what is the water storage in the soil likely to look like? What likely to look like as we go into the future? And again, you can see for those 3 socioeconomic pathways, the annual soil moisture is going to drop as we go into through the century. And not only will it drop regardless of which socioeconomic pathway we're on, but in that worst case scenario or business as usual scenario, you can see the soil moisture drops much more than the other futures. That's the trend we're likely to be seeing as we go into the future. And
I have
again,
a question.
Yes.
How did you measure soil moisture? Is that an average? Some kind of average or what?
yeah, they measure that as an average soil moisture per month.
Okay.
Okay,
Thank you.
no problem. Again, we can see Josephine County exhibiting the same trend. Now, there are other trends that we're seeing and will continue to see as we go into the future. In addition to the summers getting warmer than the winters, winters are going to get just slightly wetter and summers slightly drier. Now, when I explain this to folks, very often they say, well, it doesn't rain much here in the summer anyway. Well, unfortunately, as we go through into the future, that summer rainfall is likely to be even less. In addition to that seasonal trend, and this is a trend we're seeing already, when it rains, that rain that falls is likely to be falling more often as heavy downpours rather than that lovely, delightful, gentle rain that replenishes soil moisture. And if you think about that distinction for a moment, you'll realize the risk of severe floods increases, the risk of soil erosion increases, and the risk of trees getting toppled by those severe thunderstorms increases. And the other trend, which we are already seeing, which is likely to become exacerbated into the future, is that precipitation is likely to fall at a lower elevation as rain rather than as higher elevation as snow. And that is what explains the ongoing trend towards reduced snowpack and snow water equivalent. So we're going to look at some consequences. But first, I want to clarify an overall image of the problem that I'm talking about. Very often you will hear people talk about global warming and climate change as though those terms are interchangeable. And in fact, you will hear often folks who are a little more skeptical about climate science say, well, you know, they used to call it global warming, but that wasn't working. So they changed the name to climate change. No, that's not accurate. The first thing that happens is we get this increasing atmospheric greenhouse gas concentration, the greenhouse gases being largely carbon dioxide, methane, and nitrous oxide. That's happening in the atmosphere. That leads to the warming effect, the global warming effect. That's the primary consequence of the increasing greenhouse gas concentrations in the atmosphere. And then there's a secondary effect, which is the climate chaos that we're experiencing, the increasing frequency of really crappy weather, very hot, very dry weather. That's the climate change that we are experiencing. It's a function of the global warming, which is a function of the increased concentration of greenhouse gases in the atmosphere. That's all the atmospheric response. Another phenomenon, which is a consequence of this increasing concentration of greenhouse gases, particularly the carbon dioxide, is a phenomenon which is often associated with global warming, but it really is a different phenomenon that results from the same root cause. So I spring that off in a different direction. Carbon dioxide is absorbed in our water bodies, largely in our oceans, and that's what leads to ocean acidification. And you've probably heard about that phenomenon. And so the point I want to make is global warming is one consequence of this increasing concentration of greenhouse gases. Ocean acidification is a different consequence. Okay, I've scheduled a break here. Is it too early for a break? So why don't we see if anybody has any questions that they didn't ask as we came to this point, and then we'll take the break.
So we know now that soils also can take up a lot of the carbon dioxide, correct?
That's the soil organisms, yes.
Yeah.
The question was, we know that soils can take up a lot of the carbon dioxide. Okay,
Are there negative consequences to that as we see with the oceans? The oceans are about full. They're with their absorption potential is my understanding. I mean, or maybe they got a ways to go, but they have a limited amount that they can absorb and so the question is, are soils, is there a negative effect of soils absorbing more?
okay, so I will repeat it just in case it didn't go out. So the question is, are there negative impacts on the soil from their absorbing carbon dioxide? And the answer to that is exactly the opposite. It's a great benefit to the soils to absorb the carbon dioxide, because what they do is absorb the carbon dioxide and they turn it into organic matter. And that organic matter builds up in the soil and that retains soil moisture. So that's great for the vegetation, but it also keeps the nutrients in the soil. And it's actually a process which you might have heard of called regenerative agriculture. We're actually dramatically and massively encouraging folks to break the conventional industrial agricultural behavior of whacking fertilizers on the soil and essentially destroying the soils. We're really encouraging folks to rebuild the organic matter in the soil, and that replenishes the nutrients in the soil, and it also promotes, as I mentioned, retention of soil moisture. So it's actually a great benefit if we can get that soil to absorb ever more carbon dioxide through photosynthesis.
Alan, it looks like someone is unmuted on Zoom. Will you ask Gail to have questions?
Okay, Gail, is it a Gail? Do you have a question? Is there anyone on Zoom who would like to ask a question?
All right, I've got one for you.
All righty.
All right, from Stan Dean in the chat, I have heard that climate change results in more extreme shifts in the north-south movement of the jet stream, which gives us longer dry spells and longer hot spells, e.g. 4 wet weeks and 4 dry weeks. Is that your understanding?
That is exactly my understanding. And so the question was from Stan, just in case everybody didn't get it. Stan has heard that the process of global warming is adjusting the jet stream such that we get longer periods of drought and long periods of heat. And that's exactly our understanding of what's happening. The pattern of the jet stream, which, as you may or may not know, generally flows from west to east. The speed and the directness of that jet stream, which essentially separates the cold Arctic air from the warmer temperate air, the speed and directness of that is driven by the difference in temperature between the Arctic and the temperate region. And as we are going through global warming, what we're experiencing is the Arctic region is warming much faster than the temperate region. So the North Pole that area is warming faster than we are down here. And what you can appreciate is that's narrowing the difference in temperature on average between the Arctic region and the temperate region. And as that difference narrows, that jet stream slows down and starts waggling. And so that allows the cold Arctic air so come down south, further south, and you've probably heard those talk about the polar vortex, which is exactly what is happening. The cold Arctic air is coming down further south because of the waggle of the jet stream. And the other thing that happens is the warmer air from the temperate region, where the waggle is up, goes up into the Arctic. And so we get periods of time when, for example, Alaska has this incredible hot spell. And when we have our heat domes over here, that's probably, again, a function of the, a part, at least the jet stream showing that waggle. Okay, thanks, Stan. That's a great question. Dale,
Maybe you can hear me if I shout.
No.
Okay.
need the microphone so the Zoomers can hear you.
Thank you. I just wondered if you were going to cover, because this is a question that somebody posted on Facebook about tonight, the wind, and I think the context of that is probably the LA fires. So if you're going to cover that later, I just particularly to mention that and talk about it if you can.
I didn't actually program into the talk a discussion of the LA fires because I put this together long before the LA fires started. But I'd be happy to address that towards the end when we get to the Q&A, if to the extent that I can. Yes.
This might be a simplistic question. You mentioned, talked about the summer is warming. The trend is the summers are warming. At the same time, the summers are warming more than the winters are warming.
Yes.
Is that correct?
Yes.
Why is that? You probably explained it, but.
I did not offer an explanation for why that is, but that's simply a pattern that we are seeing. In fact, summers are warming probably 2 or 3 degrees more than winters are warming. Why that is, I can't put my finger on right away, but I'm guessing it's simply because summers tend to be warmer already, and so the impact of the increased temperature is greater there than it is during the winter. But I don't have a specific explanation for that. Okay. Any other questions? Okay. Oh, are we all back?
Yeah.
All of us who want to be.
On microphone. You pull that out of your pocket again.
No, it went off. Oh, wonder what that flashing red light is. Something.
That would be, we're out.
Bear with us, it's a battery phenomenon.
Oh, no. Oh, yeah. I'll bet it is. Yeah, no, we don't.
After that track.
Okay, that seems to be working. Okay, we're back 600 batteries later. Okay, so far I have entertained you with the likely projections for Jackson and Josephine County as we go into the future. What I'd like to do now is talk about the consequences. And I have to confess, my background is in biology. And so, not surprisingly, you have a question, Nicole. One from the chat, go for it.
All right, question is, can one predict rainfall in Southern Oregon based on the ocean temperatures and whether we are in a La Nina or an El Nino?
The El Nino and La Nina oscillation, southern oscillation, does influence the likelihood of precipitation and snowpack. I actually don't specifically recall which of those creates the higher snowpack consequence. I think it's La Nina, but I'm not 100% sure, so don't quote me on that. But it does influence the patterns here, and it does have a very small, broader impact, but it's not a vast impact across the planet. Does that address the question as best I can? If you have any questions that I don't answer satisfactorily, please don't feel uncomfortable shooting me an email, alan@socan.eco. And if I haven't answered a question, I will do the best I can to find the answer. I'm more than happy to do that. And if I don't know the answer, damn it, I should find out. Okay. It's always a message when you don't turn the equipment on, isn't there? Okay. So what I want to do starting off this biological component is talk to you a little about what biologists call biomes. Most everybody else know them as natural ecosystems. Of course, all the scientists have developed their own particular language, and I swear it's so that they know what they're talking about, but nobody else does. So when if I mention the word biome, I just think natural ecosystem. And if that doesn't immediately mean something to you, then I'll illustrate what I mean. So these are examples of biomes or natural ecosystems. Boreal coniferous forest, these are boreal coniferous forests are the forests that occur at higher elevation and up further towards the northern parts of the temperate zone. We have deciduous forest, where the trees just lose their leaves during winter. And over here we have tropical rainforest. And that's all I mean by natural ecosystems or biomes. Nothing complicated about it whatsoever. And then over here we have grasslands, tundra, and savanna. And to get savanna, I had to find a photograph, of course, from South Africa so I could show giraffes. And probably one that's very obvious to most people is desert. And I show this particular image of a desert to illustrate that deserts are not always hot. Deserts simply occur where the precipitation is very low. And there are cold deserts just as well as there are hot deserts. In fact, the Antarctica is a cold desert. Now, anybody who's traveled across the United States, and I'm going to guess many of you have, will recognize that as you cross the country from east to west, you go through coniferous forests, eastern deciduous forests, grasslands, to the Rocky Mountain evergreen forests. Then we have deserts, grasslands further north. And we have over to the Sierras, we have evergreen forests. And then if we get into California, right on the coast, we get this biome called chaparral, which is a very common phenomenon in California, particularly. Now, the question that ecologists ask is, what is it that determines where these biomes exist? And it's probably something that folks who've driven across country or even flown across country will have asked themselves as they're traveling. And that's the question I'm going to answer right now. And the answer to this question for me is a personal story. One of the things that scientists are told all the time, and you might have told them this yourselves, is don't keep drowning me with data, tell me stories. And this is something that we hear a lot from the folks who are in climate change communication. Now, when I tell a story, it's inevitably going to be a little scientific, just because that's sort of the life that I've lived. And so my story is going to be about how and why I got involved in this entire climate change arena. So what I'm going to depict for you is a graph. This was a graph that I heard about many years ago. And as a scientist, one of the things that I love is discovering how the world is organized. And when I first came across this, it really organized the planet for me in a way that was so delightful. So we're going to look at what's called Whitaker's biome or natural ecosystem chart. And what you can see here is we have mean annual temperature on one axis and precipitation on the other. These happen to be in degrees centigrade and centimeters, but don't worry your pretty heads about that. It could be in degrees Fahrenheit and inches, but the pattern would be the same. So what we're going to do is throw onto this chart slowly all the biomes on the planet. And you'll see what I mean about the planet being organized. It turns out that there are three phenomena that really determine where natural ecosystems occur. Two of them are average temperature and average precipitation. And average precipitation is really a substitute for water availability. And you can see just from the discussion we've already had this evening how these are two phenomena which are integrally tied up with the whole global warming climate change phenomena. The other factor that determines where biomes occur is soil type. Now, interestingly, one of the attributes of soil type is when a biome has existed in a location for millennia, that biome essentially creates the soil type. But that soil type is then the right soil type for that biome. So those are the three factors. But you can see immediately two of them are going to be very tied up with this whole climate phenomenon that we've been talking about. So now I want to start looking at this chart. I will point out to you that this vertical axis of the chart does the opposite thing to that which axes normally do. Axes normally go from low to high. This one is reversed, goes from high to low. I could reverse it on the chart, but that's not the way Bob Whitaker did it. So I'm following his lead. If we reverse this axis, the triangle that I'm going to show you would just be a different place. And that's essentially where all the biomes exist on the planet. It fits within that triangle. And the reason for that is these conditions up here don't exist on the planet. So let's look at this. As we come down this diagonal axis from the top to the bottom, we're looking at starting off with Arctic and alpine conditions, cold temperate conditions, warm temperate conditions, and tropical conditions. And I'm gonna place you where we live here in Jackson County. Luckily, everybody is from Jackson County, as I understood from earlier. So I'm going to look at the local historic average temperature and precipitation for us here in the Rogue Valley and the average precipitation. So the precipitation is 21.1 inches or 53.5 centimeters. And the temperature is 52.7 degrees Fahrenheit, 11.5 degrees centigrade. Excuse me. What I'm going to do now is put a little mark on the chart where those conditions exist. Okay, so this corresponds to these conditions. That's where we live. Excuse me. So, what is the natural ecosystem or biome in which we live here? And I think probably the best place to go to see it is around Emigrant Lake. That kind of gives you a sense of what the natural ecosystem would be here if Homo sapiens hadn't done all his and her wonderful work to adjust it. So we live in an area which is a sort of woodland, shrubland, grassland combination. And that's why I think Emigrant Lake is a good example. it's a good example of a woodland of trees with abundance of grass and ground cover. So let's quickly put onto this chart the other biomes, and we'll start with the extremes. If we go up into the Arctic conditions or alpine conditions, we get tundra, which is what you get if you go up high in elevation or you go towards the poles. If we go down into the bottom corner, where we have very low precipitation but hot temperatures, we're in a hot desert, the kind of desert most people think about when they think desert. And then, of course, if we come over here where it's hot and wet, we get tropical rainforest. So you can see, I think, readily from those extremes how it is that these two factors of temperature and precipitation influence the distribution of the biomes. But now what I'm going to do is, in a very complex mess, throw a whole bunch of other biomes on there at the same time. So this is where the rest of the biomes exist on the planet. And you can see how the temperature and the precipitation influence where these particular biomes exist. Now, one of the interesting attributes of this chart is if you identify somewhere on the planet where you identify what the average precipitation and the average temperature is, you can easily go to this chart and you can identify exactly what the natural ecosystem would be in that place, absent human disturbance. You wouldn't know exactly what plants and animals you would find there, excuse me, simply because, as you will appreciate, evolution has taken different directions in different parts of the world. So if we're in Australia, for example, we're not going to have the same plants and animals that we will have if we're in North America. But the basic structure of the ecosystems can be adequately described by these ideas. Does that make any sense? So, as I said, this is what got me fascinated by the whole climate change thing. My memory is probably very apocryphal, in that what I'm remembering happening is probably not the way it happened. But my recollection is I've conjured up this image that I was teaching this segment of the community ecology course at Southeast Missouri State University. And suddenly I was teaching this and suddenly it slapped me across the face. If the climate projections that we were hearing about, going back 30 years now, actually come to pass, what that's going to do is disturb tremendously the average temperature and average precipitation all across the planet, to the point that the climate where it exists now and the natural ecosystem that it supports now are going to be devastated. In other words, the climate's going to change and those natural ecosystems are going to be really compromised. And when I suddenly realized that was the point in which I says to myself, if those climate projections are accurate, then the natural ecosystems on the planet are majorly threatened. And I decided at that point, I better find out if those climate projections are credible. And I did that. And it was after I discovered that I realized now I have two unfortunate attributes. I understand the climate science and I understand the biological consequences. So I have a responsibility to try and explain to other people who don't understand what the significance of all this is. And so I've been doing that pretty much ever since.
Question from the chat, Alan?
Yes.
The question is, some scientists predict a reversal of the Earth's polarity in the relative near future. How might this impact the climate?
I don't the question was how does if there is going to be a reversal in Earth's polarity, presumably what that means is the South Pole is going to become the North Pole and the North Pole the South Pole. I do not know whether that is something that happens over time and then the poles gradually rotate, or whether it's a sudden phenomenon. If it's a sudden phenomenon, I can imagine it would be quite dramatic in its impacts. But if it's gradual, depends on how gradual. It would have to be a very slow shift for natural ecosystems to be able to keep pace. And I'm going to talk about that, keeping pace with climate change in just a moment. So I don't know whether that, I've heard about that phenomenon. I don't know whether it's expected to be sudden. Does anybody know, or slow? Maybe the person who asked the question has an answer to that.
Question really is magnetism, which is what the polar reversals are, affect climate.
So if it's simply magnetism effect, my guess is, so the suggestion was that the main consequence of that polar reversal is magnetic. I can imagine I think there are some hypotheses about bird migrations, and this may be true for whales and so forth as well, that their migrations are influenced by magnetic characteristics. I've heard that. So if that happens, I can imagine it would be very disruptive to a lot of wildlife species, but that's conjecture.
I have a question.
Yeah, go for it.
These biomes, I've seen maps of biomes or vegetative groupings will change as things get hotter. And I pictured us here in Medford, and maybe things would get more like Reading, here, hotter.
Yes.
So that was my example, but I just realized, what about the edges? What about tundra and Arctic, alpine tundra and boreal forests? They have nowhere to go.
And that's, yeah. Can everybody hear the question? Okay, so everybody in the room can hear you perfectly well. So I don't think I need to repeat the question. So I'm going to talk a little about range extension of natural ecosystems in just a moment. And if I don't address your question, please come back and whack me again, okay?
Okay.
Okay, good deal. Okay, so we're back to this Whittaker chart. And what I'm going to do is imagine where we live right now. So imagine precipitation increases a little. So what that's going to do is change our climate such that is no longer quite as appropriate it is currently for woodland. So it becomes more appropriate for a temperate coniferous forest. Now, if you want to imagine what that means, it's essentially, imagine you're driving up to Crater Lake, Crater Lake Highway, right? And you're driving from this woodland area down here up into the coniferous forest belt. That's essentially the kind of climate change that we would experience down here. On the other hand, if we go to the other direction, what you can see is we're shifting towards a desert-like condition if the precipitation drops substantially. And then again, if we adjust the temperature, if the temperature rises, we're shifting out of this woodland, shrubland, grassland community type into more of a savanna or thorn woodland. On the other hand, if we go the other way, we're shifting in the direction of a temperate deciduous or boreal coniferous forest. Now, the point that I want to stress, and I'm going to make this point again in just a few moments, is what we're talking about is the climate change. we're not saying that the vegetation type will change, because there are two problems. The first one is the speed with which these climate changes are happening. And the other limitation we're imposing on those natural ecosystems is all of the barriers we're putting up to prevent them from moving. And I usually illustrate this with, I unfortunately didn't put this slide in. When I was teaching at Southeast Missouri State University, I was doing a considerable amount of research with the State Department of Natural Resources in an area which was called Big Oak Tree State Park. And it was called Big Oak Tree State Park because, yes, indeed, it had damn big oak trees in it. And surrounding that park was agricultural land, soybeans and cotton. And it was very clear to me that if climate change happened and those oaks had the temerity to try and send their little acorns out into Farmer Jones' field, Farmer Jones was going to whack them off as soon as he saw them or she saw them. So our agricultural systems are a barrier to the ability to natural ecosystems to exhibit range shift. And then the other reality is our human infrastructure, our cities and our highways are covering the environment such that our infrastructure stands as a barrier to natural ecosystems migrating. And the third limitation that is imposed on natural ecosystems in terms of their ability to exhibit range shift is their own capacity to shift. And I want you to think about a ponderosa pine tree. Just a moment. Where do the pine cones fall? Under the tree. They don't go very far. So the rate at which, or the distance at which, a natural ecosystem can shift is limited by the dispersal potential of the propagules of the species that make up that natural community. And many of those species have a very limited capacity to exhibit range shift. Some of the seeds, of course, are carried by animals, and so their capacity to exhibit range shift may be greater depending on where the birds fly or whatever. But there are a lot of limitations imposed on the ability of natural ecosystems to simply shift as the climate's shifting, and certainly at the rate at which we are imposing that shift on the natural world. I want to illustrate that particular problem now with a study, a modeling study, which was conducted now, goodness gracious, that's nearly 20 years old. But the point that this study makes is, I think, really excellent to illustrate this point. So what I'm going to do is show you a couple of maps of the planet. And we're going to look at one on this side, which will depict our business as usual carbon dioxide concentration increasing up to about 850 parts per million. As you may or may not know, at the moment, it's about 410, 15 parts per million. Before the Industrial Revolution, it was something like 285 parts per million. And I want to stress, it's not the concentration of carbon dioxide that's causing the problem we're going to look at. It's the climate that imposes. And this on the right-hand side, you're going to see another map, and this shows a future in which the carbon dioxide concentration in the atmosphere doesn't go up quite so high. That assumes we're a bit smarter than we seem to have been up until now. Now, when you're looking at these maps, I want you to consider this: the probability of an appropriate climate existing into the future is 0 if you see an area that's red, and 1 if you see an area that's blue. Is that okay so far? And I know I'm kind of teasing you because you haven't seen the map yet. You say, well, I want to see the map. Okay. Okay, so now this is looking at a future within 500 kilometers of the current location. So the question that these maps are trying to answer is the following. Within 500 kilometers of where these natural ecosystems exist now, is there going to be any climate that they can exist in? And I think that's a reasonable question to ask because at the rate at which we're changing the climate, 500 kilometers is probably a pretty generous distance to suggest natural ecosystems can shift. They also asked the question, which I'm not going to complicate the issue with, they also asked the question in terms of anywhere on the planet. But to me, that's a meaningless question because ecosystems can't hop on an aircraft and just say, so I would like a ticket to go where the climate's right for me. Could you take me there? Okay, so here are the maps. All right, on the left-hand side, again, 850 parts per million. On the right-hand side, 550 parts per million. And this gives you an approximation of the temperature difference that this atmospheric concentration means. And this is really probably what's driving the pattern. And here we have the probable temperature that this condition is driving. So the question is, what regions of the planet are likely to be most affected? And I'm going to ask that as a genuine question, not a rhetorical question. So I just want you to popcorn up the answer, and all you got to do is look at the maps and answer the question. Where is going to be most affected? Clearly, yeah, the first thing you look at is this big blob that's Africa, big red Africa. And then you see that pretty much the tropical regions are the areas that are likely to be the most affected. I think this chart really illustrates one of the reasons why countries in the southern hemisphere are, to a large extent, so irritated at countries in the northern hemisphere, which have largely been responsible for the increase in atmospheric greenhouse gases, because they haven't had much of an impact on that, but they're the ones that are going to reap the reward for what we have been doing to the atmosphere. We can see clearly on the right-hand side, if we don't increase the temperature quite as much, things are not quite as bad. Still not really too good for Northern South America or much of Africa. Now, before I go on to look at wildfires, I do want to point out when I talk about this most often, I put it in the context of biodiversity, the species that make up those natural ecosystems. Because what we're looking at here is why global warming and its climate change consequences are having such a profound impact on species extinctions. Because that's the outcome as these natural ecosystems are compromised by the changing climate. They have two choices, right? One, they can hop on a plane and go somewhere if there's anywhere to go. Two, they can go extinct. Since option one is really not available to them, extinction is what we're tending to see happening. So this is why you've probably heard the explanation or the argument that we're currently experiencing what's called the sixth extinction. there have been 5 major extinctions in the history of life on the planet, and in which something like 90% of the species have been extirpated from the planet. And we, because of the global warming climate change consequences, are on the verge of imposing that on the planet again, the 6th extinction.
So I have a question,
Yeah,
going back to that, okay, on the 5-degree C change, if we go back, if you go back to your previous, the winter thing, 5 degrees C would pretty much wipe out the tundra, so I'm surprised to see if they're across the top that they still have it blue, that they think there would still be area available for tundra to exist. Because you've lost, I mean, it doesn't get cold enough. That 5 degrees C, based on the other.
based on the Whitaker chart.
Yeah.
Yeah, it is, and I would agree. I'm a little surprised that we have this little blob here where the probability is 1. That it seems a little optimistic. I'm not going to disagree with you there.
Well, that's, okay, that's my view.
Yeah, okay. Fair enough. Okay, so as I said, when I talk about this, I'm usually couching this just because my background is biology, ecology, conservation biology. I couch it in terms of biodiversity. But I know there are folks out there who actually don't care about the biodiversity on the planet. And so my response to that lack of concern is, these are exactly the same variables that influence our agricultural systems, and as I'll show you in a few moments, our forestry systems and our fisheries. And so even if you don't care about biodiversity, maybe you like eating every once in a while. Because this illustrates what the threat is to the agricultural systems across the planet. So much of Africa is going to find itself really compromised in terms of food production. Okay, I think it would be remiss of me, even before LA found itself in a conflagration. I even back then, I thought it would be remiss of me to not talk about wildfires. So let's look at what's happening in the Western United States. These are the kind of charts I think most people are familiar with. If we look at the acres burning in the West from about 1970 through 2014, I'm afraid this chart, yes, it is about a decade out of date, but you've probably seen these kinds of graphs before. And if we look at the number of mega fires, those are fires over 1,000 acres, you can see essentially the same pattern. And the thing that we notice is when you come across these graphs, normally they do start around 1970. Which I think begs the question, so what was going on before that? So let's go back a little further and look at wildfires in the USA in terms of millions of acres burned. Okay, so now go back to 1970, and this is the pattern. Go back a century, and what we see is, we're going to circulate these slides so don't feel you have to memorize them or photograph them. Okay, so if we go back further, you can see this immense area burned back to the early part of the last century. Even what we've been experiencing over the recent years is relatively little, and that doesn't count 1920, notice, because this doesn't go up to 1920 or 2020. But look at that, this kind of pattern, and I'm going to talk about that just a little more in a second. So one of the things that happened in 1942, Bambi. Everybody remember? No, you don't all have to remember Bambi. I'm not going to challenge you to all remember that. But Bambi was on loan from Disney as the poster child for fire prevention. And then along came Smokey Bear. Now you will often hear people talk about this character as Smokey the Bear. Smokey Bear, there's no the in it, it's Smokey Bear. Smokey was actually invented in 1944 in response to the threat that the Japanese would drop incendiary bombs on the forests of Western US and set them all on fire. So the Forest Service invented Smokey to help counter that potential threat. And that happened in the early 40s. Now, what we're looking at here is the frequency of fire in, this is the Rogue Valley, in case that's not immediately obvious to you. And what we're looking at here is the historical frequency at which fire occurred on any given place, in any given place. And so we're looking at here 2 to 26, every 2 to 26 years, every 12 to 29, every 4 to 19, every 3 to 26. On average, the fire return interval, which is what this is measuring, was something like 8 to 10 years. So if you stand in a given spot, every 8 to 10 years, you're going to get fried on average in the dry forests of the Rogue Valley. Now, if you're in the moister forests at higher elevations, the fires historically were not as frequent. But down here, they were very frequent in these dry forests, which is where most of us live these days. This is a Douglas fir tree that Kathy and I stumbled across as we were out on a hike in Coos County. And this illustrates the history. What you can see here is in the tree rings, you can see embedded the evidence of those historical wildfires. You can see how frequent they were back here. So we're looking at that, the representation of that fire every 8 to 10 years or so. But from here onwards, nary a fire. We have been incredibly successful at suppressing fire. This in a system, again, reminding you that is fire dependent. And when we suppress fire, again, what I mentioned earlier, what we are doing is allowing the invasion into the forests of species that are intolerant of fire. And so the vegetation in that forest builds up. This is a rather busy graph, and I know that, but I'll walk you through it step at a time. What we're looking at here is the Oregon Department of Forestry fire history from 1911 till 2022. We're looking at what I'm going to draw to your attention is two factors here. One is the area burned, and that's illustrated by the bars going upwards here. Notice how this looks very similar to the one that we looked at 2 or 3 slides back of area burned across the United States. So we go back to the early decades of last century, and we are looking at areas, vast areas burned. And then we come into current, the more recent period, 1970 onwards. Now we do get a sense of how odd 2020 was, right? It sort of put us back in this kind of area burn territory. But that was a very odd year compared to the rest of the years around here. So let's ask ourselves what's been happening as we go through this period. There was a period here where there's a vast area burn, then it dropped, and then sort of started to rise again from about the 1970s. Yeah.
So that 1920s through the 40s and 50s was, you think like any of like the land clearing and home, especially in Oregon, and home building and everything had effect, or is this just all wildfire?
these are wildfires, and I'm going to talk about the cause and effect as I read the evidence in just a moment. I was just about to get there. But if I haven't addressed the question that you have, again, please hit me with it again. Oh, I guess, thank you, Nicole. Nicole thinks I'm sliding out of the screen. Trying to get away from the camera. Okay, so here we have large areas burned. Now, that's the brown bars. The white line, on the other hand, is fire initiations. And I think it's interesting to note that fire initiations certainly have exhibited variability as we go through the system. But on the whole, fire initiations haven't shown much of a pattern. It's not a serious trend. It's been pretty consistent. What changes is not the number of fires that start, but how much area they burn once they start. Back here, the area was huge, and it's sort of been getting huger more recently. So let's look at history. So if we look along this axis here, I'm going to depict something called the Pacific Decadal Oscillation, which is a climatic phenomenon. The Pacific Decadal Oscillation is a phenomenon that happens in the northern Pacific Ocean, and it shifts from what's called a cool, moist phase to a warm, dry phase. And it shifts every few years, sort of not quite decadally, but a little more than that. And so what we had here was a Pacific Decadal warm period where it was warmer and drier. And so notice how that correlates with that period when the area burned was huge. So when the climate is warmer and drier, the inference that we draw is that's when the risk of those fires becoming mega fires increases. Okay, then around 1940, remember what happened around 1944? Smokey Bear. So then, I mean, we've been putting fires out for decades, but that's when the Smokey Bear campaign really took off. And concurrently with that, notice that Pacific Decadal Oscillation shifted to a cool, moist phase. So it's not going to be very easy for us to tease out the impact of that natural climatic oscillation, the PDO, from Smokey and our fire suppression. It's probable that both things are concurrently impacting fire risk. So we went through this PDO cool phase, and then when we got to 1970-ish, that's when we went back into a PDO warm and dry phase. Now, whenever we look at, and I should have drawn your attention to this when we were looking at the charts earlier, whenever we look at climate trends, what we find is they really start to become evident in the 1970s. And so somewhere around 1970, 80, 90, that's when the global warming phenomenon started to have a really profound impact and a detectable impact on our global climate. And so what probably is happening here is that the Pacific Decadal Oscillation has been superseded by global warming. And so we've had this really ongoing over the last few years, particularly really serious problem of vast areas being burned. This kind of analysis has been conducted now going back 1,400 years. In fact, they've done this analysis back to 3,000 years. And what we're looking at here is area burned, which is the red line, and what climatic studies suggest the area should have been as it was being burned. Excuse me. And you can see that the climatic models really follow the actual area burned pretty closely. Does that seem reasonable to infer? And so that dotted black line and the red line are pretty consistent up until very recently, when the climatic suggestion of area burn, of what the area burning should be, look, has suddenly risen. That's the recent global warming effect. And so what the people who conduct these studies argue is they point to this amplitude of climate-driven variability in area burned, and then they point to this area up here and they say, whoa, we're in a huge fire deficit. Given the climate that we currently experience, we should be experiencing much larger areas of our forests burning. And I think the folks, I mean, the 2020 Alameda fire is probably in part, at least, the representation of this risk. If we look at the projected increase in area burned as we go into the future, this is answering a question: what would a 2.2 degree Fahrenheit increase above the 1961-1990 average do to the area burned? Likely. And what you can see is, for us, what are we down in here? The area burned is likely to be up in the what? 3 to 4 or 4 to 500% more than it is now. Entirely consistent with that slide I just showed. So I don't think there's any doubt that as horrendous as we think the fire risk is now, if we don't do something about global warming and the climate consequences, it's gonna get worse. The main factors influencing our wildfire risk are climate and fire suppression. And I mentioned this before. If we keep suppressing fire and allowing into our forests more and more vegetation, what we're doing, and the wildfire folks call it fuel for obvious reasons. That's one of the factors. The other thing is early snowmelt and early warm season reduce late season runoff. They dry the soils and vegetation and increase the fire risk. Early snowmelt is exactly what we're seeing. And it's early snowmelt, remember, of less and less snow at higher elevations. This little datum point really surprised me. The difference between a bad fire season and average fire season is only about 1.8 degrees Fahrenheit during the growing season. It's not a phenomenal difference. The Western fire season is now, what, 3 months longer than it was in the 1970s. This is the representation of exactly what I was talking about, the impacts of global warming starting in the 1970s. Let's have a quick look at an agricultural implication. Okay, I'm going to try and speed up a little because what, we've only got 10 minutes left, right? Okay, this is a graph of the optimum growing season for grape varietals. And I'm a big fan of grape varietals. Many of you are here too, probably. So this is the average 1961 to 1990 temperature. And you can see these are the grape varietals that were experiencing optimum conditions for the growing season. But if we go towards the end of the century, the climate here is going to be like that. And if it's even more extreme than that, will be good for table grapes and raisins. It's kind of interesting to look at the grape varietals that vineyards around this area currently grow, because it does seem these data, I should say, come from Greg Jones, who was in the environmental science department at SOU. And I don't know whether Greg got to the vineyard growers, vineyard people here, or whether they are just smart and they read about it. But it's interesting, if you look at the grape varietals that are growing these days, you'll see Tempranillos and Cabernet Francs and Sauvignon Blancs, warmer season wines. Folks here have seemingly become aware of the trends, and they've started to grow the varietals that prefer the warmer conditions. I think from an agricultural point of view, this graph is illustrative of what folks who are in agriculture should be thinking about. Because whatever crop you're growing, what you have to be doing is thinking about what varietals are there out there that prefer warmer conditions. Chris Hardy, some of you may have heard of, is experimenting with this in relation to grains. He's trying to grow grains in this area from across the world and exploring which grains seem to be doing well. And he's found some grains from very dry areas which are doing pretty well here. Let's have a quick zip through some forestry implications. This is the Douglas fir optimum distribution now, climate and its distribution now. So this is Oregon as a whole. See, coastally, there's a large amount of Douglas fir. The sort of deep burgundy color is where it's doing well. And as we go through green into yellow, it's doing less and less well. Let's look at what the future climate is likely to do to the Douglas fir. Now, you've heard about Douglas fir death, which is happening in this area. I would suggest that is a current representation of exactly what we're seeing in these climate models into the future. The climate is shifting out of the range for Douglas fir in many parts of this part of the world. Ponderosa pine now, again, by the end of the century, the ponderosa pine, which is generally considered to be a drier climatic species, is not going to be doing tremendously well by the end of the century. Let's look at some other. Here's the Pacific madrone. Where is the climate appropriate for Pacific madrone by the end of the century? Just kind of congealing down towards the southwest border with California. This one is a little more disturbing. Lodgepole pine, Sitka spruce, and western hemlock. End of the century. Oregon is likely to be outside the range of lodgepole pine and Sitka spruce. How about white oak? I think I might have a white oak coming up. I'm not sure. Engelmann spruce and subalpine fir. Western juniper. I started to look for what species are likely to be doing better. I was thinking the western juniper might be one, but apparently not. I'm afraid I didn't include the oaks. What seems to be happening, seems to be projected to happen with oaks is their tolerance range expands, but the optimum conditions contract. I'm just getting in towards the end. What this slide is illustrating is annual fossil carbon dioxide emissions. And what we're looking at here is which nations are responsible for the problem. And as you're probably aware, China has certainly outstripped the United States in terms of its total emissions. And India is coming up close behind. All the others are about this, a bit above China. This is 2024. This one illustrates what it is we burn that causes the problem, and you can see coal, oil, gas. That's the thing called natural gas. The thing that the gas utilities keep trying to tell us is the clean fossil fuel. Not at all. Because of the methane that is basically natural gas and its leakage, and because methane is over 80 times worse than carbon dioxide in terms of causing global warming, burning gas is pretty much as bad as burning coal. And these are trends in the United States in terms of our energy sources. Fortunately, renewables are increasing. You can see nuclear pretty much holding steady. Natural gas, unfortunately, has increased substantially, and coal is decreasing, at least. Okay, so what are my general implications? And then I'm going to get to the three things that I'm going to urge you to think about. If we don't divert our global climate trajectory, in my judgment, a sustainable future will not be an option. There is a bill that's going through the Oregon legislature introduced by our Senator, Jeff Golden, which seeks a referral to the people of a constitutional amendment providing Oregonians with the right to a healthy environment. That's something that I personally think is very well worth supporting. And here we are for 3 additional actions that you might consider. One of the things that Southern Oregon Climate Action Now has been doing for several years has been teaching a course, a community course called Master Climate Protector. It was a 10-week course offered during the February through April-May period. It was offered to community members. Last year, we managed to persuade the Department of the Environmental Science, Policy and Sustainability Department to offer the same basic course as Living with Climate Change in the Rogue Valley. It's a 10-week course available to SOU students they get 3 credits, and it's also available to community members. So if you're interested in learning more about the cause for this global warming climate change problem and what we can do about it, then I would encourage you to have a look at that website and consider signing up. We are going to be starting the course in April, I think is April the 2nd. It's going to be running Wednesday evenings, 5:30 to 8:30, and it runs through June. The second thing we're going to encourage you to do is get off do what you can to get off fossil fuels by electrifying everything you can. And you might reasonably say, but wait a minute, isn't a lot of our electricity produced by coal-fired power plants? Yes, now. But thanks to our House Representative, Pam Marsh, introducing a bill back in 2021, which coincidentally was House Bill 2021. Electricity retailed in Oregon by 2040 will have to be 100% produced from renewable sources. So our electricity is getting cleaner and cleaner and cleaner, and electrical motors, generally speaking, are much more efficient than internal combustion engine equipment. So please try and get off fossil fuels. We have, I think at the back, don't we have a brochure of individual things that you could consider doing if you really want to get personally involved. The third thing, the Oregon legislative session started yesterday, runs through the end of June. It's called the long session. Consider engaging through SOCAN's federal and state project team if you're interested in getting involved in legislation. There's a whole slew of legislative items coming through which pertain to the entire climate issue. And if you think you're interested in getting involved, please consider that. And there's a website, and you're going to get this information from Nicole after the class. Please consider joining us in combating climate change. I really think unless we address climate change, there's nothing we can do to live sustainably. And that is my presentation. So I don't know what our demand is for being evicted from the building, but I'm happy to sit around and chat if folks want to talk and ask questions.
There are a couple questions in the chat
Okay.
from Pete. Restoration practitioners discuss assisted migration when selecting native plant material genetics for outplanting. While the individual sites may benefit with increased survival under climate disruption, will this inoculation have a regional effect?
Assisted migration is a fascinating question, and I've been hearing about this idea probably for decades. And just to clarify, assisted migration means, I think the question implied this, but in case it wasn't obvious, it implies when you're planting, you bring varietals from an area that is warmer and drier than historically has been the area where they're being planted. And a lot of folks have tried this. The catch with assisted migration is what you're doing is planting seedlings of, let's say, tree species that are there. You're planting seedlings that should be, if they grow, appropriate for the climate that is going to exist in that location 20 or 30 years from now. Are those seedlings going to survive long enough to be there in 20 or 30 years' time? That's a key question to which we don't have an answer, because we're taking them out of their optimum condition and putting them into a suboptimal condition. And the second problem with assisted migration is that it almost presupposes we know what the climatic conditions are going to be like 20 or 30 years down the road. And as you can see from those three scenarios that I depicted right at the beginning, we don't know for certain what trajectory we're going to follow. So we're not real. My concern is we're not really smart enough to know where we should get those propagules from to plant here in the future. So I think it's probably a worthwhile experiment to try assisted migration, but we have to recognize it's fraught with hazard. Okay, was there another question?
Yes, a question from Doug. Plants need lower night temperatures to rest. Are the low temperatures at night increasing faster than the high temperatures during the day? And if so, should we pay more attention to the effect on various plant species and biodiversity?
I can't remember absolutely for certain, but I think nighttime temperatures might actually be increasing faster than daytime temperatures. And I'm not don't quote me on that because I'm not 100% sure. So that to the extent that the premise of that question is accurate, it suggests that is likely to be a real problem. We should be definitely looking at that as we try and figure out what's going to be happening into the future.
Are there more questions in the audience?
Yo,
Asked a question about the LA fires. I'd like you to try and address that, but also apply it here. Because that kind of wind from the east, a very dry wind, was pushing the Alameda fire, as well as on the same day, the Slater fire, and that one went 31 miles in a day.
it's a fascinating parallel. I think there is a lot of similarity between what's happening in LA and what we experienced in, was it 2020? It was, or 2020 or 2021?
2020.
2020, so it was the COVID year as well. And that those Santa Ana conditions, those heavy winds are driven by a high pressure area occurring in the high desert and a low pressure area occurring out in the ocean. And so a high pressure area is when the air is dropping, hence high pressure. A low pressure area is where the air is rising. And so the wind blows from here over to here. And if the difference between the low pressure, low pressure area here and the high pressure area here is great, then those winds are going to blow mighty fast. And global warming is probably increasing the frequency of these low pressure areas and these high pressure areas and potentially the intensity. So I'm guessing that the global warming had a profound impact both on the Alameda situation and LA. Kathy.
I think one thing that's missing is we don't have to go on those trajectories that we saw. And to me, the answer is doing something so we don't. And that's the action part.
Yes.
So
Yeah.
that people get really bent out of shape with it's so bad. Well, let's do something so it's not so bad. That's what we can do.
I was trying to make that point earlier. We don't have to follow the worst case business as usual scenario. We can be smarter than that. But I didn't keep making it, and it's probably as well that I keep making it. And thank you, Kathy, for bringing it up again. Okay.
Thank you, Alan. I don't see any more questions in the chat, but I see a lot of thank yous. So it's very
Okay, well, thank you all for coming, whether it was via Zoom or via ambulation. Thank you.
These last couple.
All right, thank you everyone on Zoom. Have a great evening.
We just down here, not a tomato growing area. So I was determined to go to the first year of beginner's life.